It's November 30th, 2020. I'm Todd Dunn, and today I'm going to be doing my second video in my series on repowering a displacement hull powerboat. In my first video, I talked about some simple formulas using only the waterline length and the displacement to estimate how much power you would need. And those formulas will usually get you in the ballpark for picking an engine. However, there are more accurate ways to do it, and they range from very, very accurate if you have a few $1,000s and can afford to buy one of the numerical naval architecture programs, to somewhat less accurate, but still pretty good if you want to use a little bit simpler approach. So what I'm going to do today is present one of the more accurate but still relatively simple approaches to calculating just how much power you need to move your boat. And that's going to lead into my next video, which will be on how to pick and size your propeller. So, how am I going to do it? Well, I'm going to follow this relatively simple introductory naval architecture book, Principles of Yacht Design by Larsson and Eliasson. This is the 1994 edition. There is a newer edition available, but this particular one has all of the terms and all of the methods laid out very nicely so that I think anybody can follow them. So we'll use this book, and I'm going to talk about how to go about doing this power calculation. So let's get started.
Okay, now relative to the simple methods I used in the last video to calculate required power, this method takes into account a number of parameters about the shape of the boat's hull. And we're going to get those parameters from a lines drawing for the hull. But before I show you the lines drawing, I'm going to go through and define the various variables that we're going to need. And they're pretty simple. The first one is the waterline length of the boat. In other words, the length of the boat at the waterline. And then the beam of the boat at the waterline. This is the maximum width of the boat at the waterline. And then we want to know how deep the body of the hull extends into the water, which is called, that part, the body of the hull is called the canoe body. So we're going to look at the canoe body draft, and that is the draft exclusive of keel, rudder, propeller, and other appendages. And the next variable we're going to need is boat speed. And then we need two related variables. One is the displacement of the canoe body of the hull, but expressed as weight in kilograms. And then the volume displacement of the canoe body of the hull. In other words, what is the volume of the underwater part of the hull? And that'll be expressed in cubic meters. I should say that I'm using metric here because the method described in Principles of Yacht Design is all in metric. The next number is what's called the water plane area. The water plane is as if you took the boat and cut it off right at the water line and then looked at the area of the boat right at the water line. That would be the water plane. And finally, longitudinal center of buoyancy. Wow, it's a big term. What's it mean? Basically, this is the point fore and aft in the hull where the volume of the submerged part of the boat is the same forward and aft of that point. Well, the source of the numbers that we need to do these calculations is a lines drawing of the boat. Now this is a lines drawing of my boat, Tortuga, and this drawing has 3 parts. It's a typical one. Up on the top we have a plan view of the boat. This is just looking down at the boat from above, what it would look like. And usually it just shows the outline of the boat, and with maybe some other features, like I've got the cabin top in here and a couple of hatches. Below that we have what's called an elevation view. This is looking at the boat from the side, and normally these elevation views show the way the boat would look right down the center if you were able to look only at the outline of the boat from the center. And I have put the cabin house on here, and there's a little bit of additional information because I drew this particular lines drawing to build a model of my boat from. Now, in the elevation, there are a couple of important pieces of information. One is these vertical lines here are what are called station lines, and they are the locations where we're going to look at the athwartships or side-to-side shape of the hull. So basically, if we were to slice the boat along one of these vertical lines and look at the outside edge of the hull, that would be what we're going to use these lines for. We can also see here the dark blue line is the water line. In this case, it's the design water line, whereas is where the designer of the boat wanted the water line to be. And then below that, I have a light blue line, which is the actual measured water line on my boat. Now, a normal lines drawing wouldn't have this because you would have to be able to put the boat in the water and measure the actual water line and compare it to the real water line to get this data, but I have it for my boat. Now, also in here, we can see the shape of the hull below the waterline, and you can see several parts. The main part of the hull from the waterline down is called the canoe body, and this is the underwater part of the hull that does not include the keel or the rudder or any other appendages like the propeller or anything. So that's the canoe body, and we can measure in the elevation, we can measure the waterline length just by measuring the length of the hull at the waterline, and we can measure the canoe body draft by measuring from the waterline down to the deepest part of the canoe body. So those are 2 of our numbers we can measure directly off of the lines drawing. Now, the other numbers are going to be a little bit more complex, and we are going to have to use the next part of the lines drawing to do some calculations. And that is the right-hand part here. That is the body plan. Now, this drawing shows the body plan a little more closely. And what the body plan is a series of lines that show the shape of the outside of the hull at the stations from the elevation. So at each station, if we took a slice, a vertical slice through the hull perpendicular to the length of the boat, and then looked at the shape of the outside of the hull, that would generate these lines. Now on the right hand side of this diagram are the shapes of the hull starting at the bow and moving to the midpoint or midships point on the hull. And on the left-hand side are the shapes of the hull starting at the outermost line at midships and moving aft to the aft end of the boat, or transom in this case. And you can also see the water line, which is labeled 0 here. And there are also some other horizontal lines labeled 1, 2, 3, 4, and in this case also -1. And those are also called water lines, but the one at 0 is the design water line, which is the one we would use. Now, along the 0 line, if we were to take a slice through the boat right along that line, parallel to the water surface, and look at the outline of the hull, that would be the water plane. And we can calculate the shape of the water plane by just measuring out from the center of this diagram to each of these hull forms at the different stations and making a mark, going all the way out, then starting back at the aft end of the boat and going all the way to the transom and connecting those lines up, and that'll give us the shape of the water plane. And I'll show you what it looks like. Okay, here's the water plane drawn from the body plan and the stations as shown on the elevation. And basically this is the shape of the outside of the hull at the waterline. Now we are going to have to use this to calculate the area of the water plane, because that's a parameter we're going to need for our calculations. And you can do that fairly easily. The book, Principles of Yacht Design, describes some numerical methods or graphical methods you can use. And if you have a CAD program, you can draw this to scale and just pull it into your CAD program and get the area directly, which is what I did. Okay. Now, if we go back to the lines drawing, we can use the information in the elevation and the body plan to calculate the other parameters we need. The volume displacement, the weight displacement of the boat, and the longitudinal center of buoyancy. And the techniques are relatively straightforward. If you have a CAD program, if you don't have a CAD program, then there are numerical techniques, and the Principles of Yacht Design book explains how to do those calculations and actually gives worked examples. So it's very straightforward, although if you do the numerical methods, they are kind of tedious. Once you've used the lines diagram to calculate the various parameters that I've just discussed, you can move on and calculate a few additional, somewhat more complex parameters that we're going to need from those parameters, and I'll talk about those right now. Okay, there are three more parameters that we're going to need. The first one is called the prismatic coefficient. We can calculate this one from the water plane area, the waterline length, and the volume displacement of the boat. So that's a relatively straightforward calculation once you have the input numbers. The next number you're going to need is what's called the Froude number. It's a very simple relationship between boat speed and the waterline length of the boat. And as you can see, it's very simple. It's just boat speed divided by the square root of the product of the acceleration of gravity and the waterline length of the boat. So boat speed is a parameter we change during the calculation, and we'll know the waterline length from the lines drawing, and acceleration of gravity is a constant. Okay, the last thing we're going to need to know is the Reynolds number for naval architecture, and that is simply the product of the speed of the boat and 0.7 times the waterline length divided by the kinematic viscosity of the water. And kinematic viscosity of the water depends on temperature, but the dependence does not have a huge effect on the calculations. So we'll simply use the value at 20 degrees C, which is 1 times 10 to the minus 6 meters squared per second. Okay, now that we have all of the variables that we need, and we've used our lines diagram to extract them, either directly or by calculation, we can go ahead and calculate the amount of power needed to move the boat through the water. And this is done in three parts. Those parts are frictional resistance, in other words, friction between the water and the hull as the boat moves, wind resistance of the above water part of the boat as it moves through the air, and finally wave making and viscous resistance. So we're going to have three equations that we'll solve. They're relative. The first two are very simple. Frictional resistance is just given by a frictional coefficient, which you can see here is calculated from the Reynolds number. So it's going to be a function of boat speed times 0.5 times the density of seawater, which is 1,025 kilograms per cubic meter, times the square of boat speed times the wetted surface area of the canoe body of the hull. And this is just the area of the outside of the canoe body of the hull. And that's pretty straightforward to calculate, again, from the lines drawing. Then there's wind resistance. This is very, very similar to the frictional resistance. And basically it's given by 0.5 times the density of air, which is 1.204 kilograms per cubic meter at 20 degrees Celsius, or 68 degrees Fahrenheit, times the apparent wind speed, which we usually use the still air case, so that's just how fast the boat is going, times a wind resistance coefficient, which is assumed to be 0.5 for these calculations, and that's multiplied by the maximum cross-sectional area of the above water part of the boat, which is the hull and anything that extends above the hull in the form of a cabin or a mast. So we just calculate those cross-sectional areas and plug those numbers in, and we can calculate the wind resistance. And we do both the frictional resistance and wind resistance by simply varying boat speed and do the calculations for discrete boat speeds. Now we come to the slightly more complex calculation. This is residuary resistance due to wave making and viscous pressure on the hull as the boat moves. And this is where we're going to put in most of our hull shape parameters. Our prismatic coefficient, longitudinal center of buoyancy, the displacement, the waterline length, the beam at the waterline, the canoe body draft, etc. Now this calculation is done in two parts. The first part is the low speed part, and if you remember the Froude number, which is an expression of boat speed relative to the waterline length, that's the discriminating parameter for the two parts of the calculation. The low speed part of the calculation is for Froude numbers up to 0.45. Now 0.45 is a little bit faster than the hull speed, which, if you'll recall, is 1.34 times the square root of the waterline length of the boat in feet, where the hull speed is given in knots. So up to a little bit faster than the hull speed, we're going to use the first equation here, and then if you want to go faster than hull speed, we're going to use the second equation here, which is for Froude numbers from about 0.45 to 0.75, which is maybe up to about 1.5 times hull speed. The first equation has 10 terms, a constant and 9 terms multiplied by 9 additional constants. Now what makes this a little more complex is the constants depend on boat speed expressed as Froude number. And so you're going to have a big matrix of constants, and depending on how fast you're going, you have to pull out the appropriate constants. So what you do is you use your boat speed and the waterline length to calculate the Froude number. That tells you which constants to use, and you plug the constants in along with all the other variables and pull out a residuary resistance number. And when you get up to speeds corresponding to Froude numbers above 0.45, you move to the second equation, which is a little bit more simpler. It has only 6 constants that you have to pull out of a matrix. Again, the matrix depends on Froude number, so which constants you use depend on how fast the boat's going. So if your boat speed is in the range of Froude numbers from 0.45 to 0.75, you calculate the Froude number, choose the appropriate constants, and calculate the total resistance. I'm not going to go through the terms in detail, just be a little bit confusing, but if you want to see what they are, you can pause the video and look at these two equations in detail and maybe even write them down if you want. I am not going to give you the constants because there are about 150 of them, and you need to find a copy of Principles of Yacht Design 1994 edition and look at the tables in Chapter 5 to get those constants. So let's go on and look at what the results of these calculations look like. This diagram shows the results of the resistance calculations. Now these were done from my boat, which is a 32-foot boat, and I used a 10,000-pound displacement for the calculation. I pulled all the numbers that went into the calculation from the line drawing for my boat. And what we have here is calculated resistance versus boat speed. This boat speed is the input parameter that we change in increments to get these curves. Now, you can see there are 4 lines here. 3 of them are the calculated resistances for air resistance, frictional resistance, and residuary or wave making and viscous resistance. The bottom line in green is the air resistance curve. So you can see that curve is really a small contributor to overall resistance. So unless your boat has a really big bluff cabin house, air resistance isn't going to be a big factor until the wind is blowing really hard. Now this calculation was done for still air, where there's no wind and the only air resistance is due to the movement of the boat. If you wanted to redo the calculation for going into a headwind, you could simply add the headwind to the speed you use to do the calculation, and this number would go up, and you could see what the effect would be. The next line on here we want to talk about is the black line. That is the frictional resistance curve. You can see it increases more or less continuously. The rate of increase gets a little bit bigger as you go faster, but it isn't a huge change. But it is the largest single contributor to total resistance at lower speeds. And coincidentally, it's the largest contributor up to just about hull speed for most displacement hull boats. And finally, we have the red curve. This is the wave making or residuary resistance curve. And this curve is not that important at low speeds, but once we get up to hull speed, it becomes the most important contributor to total resistance. And as you can see, that red curve, once we cross over the frictional curve in black, goes up very dramatically and becomes the dominant factor in total resistance to movement. And finally, the blue curve is the sum of the 3 components, and you can see how it doesn't take a lot to move the boat up to pretty close to hull speed, and then it goes up dramatically as we get very small increments in boat speed. For example, at 7 knots, we're looking at about 1,300 newtons, and at 8 knots, we're looking at 2,000. So that's a 50% increase for 1 knot, and that will show up in how much power you need to move the boat, and also in fuel consumption. So this is the result that we're going to get from these calculations. The calculations, however, are resistance to movement in newtons, not horsepower or kilowatts. Now we can convert these roughly into horsepower or kilowatts by simply multiplying the resistance at any given speed by the boat speed in meters per second, and that'll give us the required the power in watts, which we can easily convert to horsepower by simply dividing by 746. However, this is the power at the propeller. And propellers are not 100% efficient, so this does not tell us how much engine power we need. In order to get engine power, we're going to have to, one, determine exactly what kind of propeller we want to use, what diameter, blade count, pitch, etc. We're going to want to factor in the gear reduction in the transmission, and then we can calculate the actual engine horsepower required to turn the propeller fast enough to move the boat at any given speed. And that will be the topic of my next video. So anyway, I hope that you found this interesting and that you got something out of it. And if you feel like acquiring a copy of Principles of Yacht Design, the 1994 edition, you can do these calculations yourself. They are not that difficult. And after you see my next video, you'll be able to figure out exactly how much power your boat needs to go at different speeds and what the details of your propeller will be. Anyway, so thanks for watching. Hope you enjoyed it. If you did, please give me a thumbs up. And don't forget to subscribe to my channel and click that notification bell.